Okay, so yeah, it's the end. Well, I guess it's week 5, and it's our second lecture in week 5. So things are wrapping up. We would normally have a lecture on Monday of 6th week, and then you would take your final exam on Wednesday of 6th week. So, but Monday is a holiday; it's Labor Day. So there's no class on Monday. So what I'm doing is I'm gonna have a review session on Friday, just because I think it's useful for you guys to kind of have a review session. And so so I'm gonna just kind of do that. It's like I don't get extra pay for doing that or something, but I'm happy to do this. So on Friday, I'm gonna have a review session at noon. It'll go from noon to 1:50. If you can make it, great. And if you can't, I'll record the video and I'll post it. There's no lecture viewing quiz or something like that. So I think it'll be helpful, and I think you should watch it. And so during that review session, I will go over the what the final exam will look like. But basically, uh, it's going to be on Wednesday of week 6. You'll log and it's the same. It's synchronous. Okay, so some of you live in other time zones, and I apologize for this. This will be kind of just the one thing the entire quarter where it's synchronous, and you kind of have to be here during that period. Now, if there's something going on and you seriously cannot make it during that time, send me a message on Campus Wire, and sorry for the beeping there. Send me a message on Campus Wire, and we'll try to work something out. But other than that, yes, it'll be synchronous on Wednesday, and you'll log in on Zoom just with your cameras on. And that's kind of how we'll do the proctoring. It's open note, open book. You can use a calculator. You can use R as a calculator. The only thing you're not allowed to do is like work with other students. And so the proctoring via Zoom is really kind of just to make sure you're working by yourself. And I don't think this is a major issue, but I know, like, I've heard stories of kind of students getting together and taking the final exam as a group or something, and that's not okay, right? So anyway, proctoring will be done via Zoom. You'll just log in like you guys are logged in right now. You'll turn on your cameras. You'll stay muted, and then as soon as you're done with the exam, you'll sign off. Exam will be taken on Gradescope, and it will be from 4 to 6 p.m. on Wednesday. There is like a little bit of a funny scheduling thing. So you'll have quiz 5 this weekend, just like every other weekend. And normally you would have quiz 5, we would have the review session on Monday, and then you would take the final exam on Wednesday. But because we have Monday Labor Day, you're gonna take quiz 5 this weekend, and then there's nothing, and then you take the final exam. So it's kind of like you have a quiz and then a final right after that. It's just kind of a little bit of a scheduling oddity. I hope that's okay. And then and during Friday's review session, I will go over kind of like what you can expect to see on the final, and we'll do some, go over some review questions and things like that. I guess, are there any questions about the logistics of the exam? Not like what kind of stuff will be covered on the exam, because I'll cover that on Friday, but any kind of just like logistical things. Any questions there? How many questions? I don't know the exact number of questions. It'll be kind of like your Gradescope quizzes. So you'll have multiple choice questions. You'll have, maybe some fill in the number questions. I guess one thing about the final is pretty much all the questions will be weighted evenly, and there'll be no partial credit. So I think like every question will probably just be like worth the same amount, and either you get the number right or you don't. And that just kind of helps with the grading, getting the grading done very, very quickly, instantly. And then, I can file your final grades fairly quickly. after that. In the past, I have not needed to do any kind of curving or adjusting of grades. So, you know, in the syllabus, I kind of lay out the points, how things are done, and we're going to stick to that. And you know, I think right now the homework average is like a 99%, or you know, like a 98%, something like that. The lab average is like a, you know, somewhere in the 90s, 90, 95 or something. The quiz average, you know, maybe a little bit lower. It's like an 89 or something is the quiz average right now. And then, you know, the final exam average is usually somewhere in the 80s or something like that. And so historically, I haven't needed to do any kind of curving or adjusting there. And the overall class average is somewhere in the mid to high 80s is the overall class average. So I feel fairly comfortable about that in terms of, you know, fairness in terms of grading there. And so so that's what we've got going on. Yeah, so for the final exam, there's you won't be turning in your scratch work. You'll just kind of take the exam, and that will be it. Okay. Oh, I do have a favor to ask of you, and that is please fill out your course evaluations. So I think, I don't know, your course evaluation, you should get an email or something, and you can rate what you think of the class and what you think of me as your instructor. And, you know, what your number ratings are helpful. And then the comments, any comments that you write are also helpful. I do read all of them. We don't get to see them until after grades are published. You know, just I guess they're worried that, you know, some professor might be angry about some comments and take it out in the grades or something like that. So we don't get to see anything that you write until after grades are sent to the registrar. But that's that. The two questions that are kind of like the most important are the ones at the very end, which say, what is your overall rating of the instructor and what is your overall rating of the course? And so whatever, you know, the highest marks you're willing to give me, I greatly appreciate that. The evals are not extra credit. Just, you know, I just have to ask, please, you know. Yeah, will there be a study guide? I don't have a specific study guide, but I think the review session on Friday will serve as kind of like, this is how you should study or what you should study. So so that will be that. I hope you guys have enjoyed the course. I hope you know, it's statistics, right? And you know, unless you're me, you know, you probably weren't like exactly looking forward to the class, but hopefully it was not as painful as, you know, you might have imagined coming in, and hopefully you feel like you got something out of it. And oh, and this week's lab is, you know, you read this journal article, and so, you know, my hope is that now you read these journal articles, and where they have that statistics section, you're not just going to skip over it and go straight to the conclusion, but like you'll be able to read it and you'll be like, oh yeah, like this kind of makes sense. So so that's the hope, right? Like you can read this and like the stuff they say about p-values and the different tests that they've done makes sense to you. Oh, thank you for that comment in the chat where you say you like the class a lot. That means a lot to me. All right, so our very last chapter in of material is chapter 12, and chapter 12 covers correlation and linear regression. Okay, and the idea here is, you know, so we've been kind of exploring relationships between variables, and now in chapter 12, we're going to look at a potential relationship between two numeric variables. Okay, and so the idea here is you have observations in your data, and each observation, you get has multiple variables recorded, and at least two of those variables are numeric, right? So you can have a person, and this person has an age and a height and a weight and a gender and I don't know, a hair color and eye color and something like that, right? So you have all of these traits recorded for each person, and you're just going to look at two of these variables that are at least numeric. So maybe you look at the relationship between height and weight, or age and height, or something like that, right? So each observation in the data has multiple variables recorded for each recording, and then at least two are numeric. All right, and so we're going to do a silly example here. Okay, so we're going to look at, I'll do some research on snakes. Okay, and we'll look at some specimens from, we'll say, one species of snake. All right, I don't know what. All right, and so we'll say here's a table, and we'll have the name of the snake. We'll have, the length of the snake, the weight of a snake. And I don't know anything about snakes, right? So, so we'll say the sex of the snake, and then, some other variable. Okay. So on and so forth. And I don't know, what are some snake names? We'll have Slytherin and I don't know, Nagini. The Salazar was not a snake, but we'll just say that's the name of the snake, right? And then we'll and we're just, I don't know how long is a snake supposed to be. All right, so we'll just make up some numbers here. All right, 60 centimeters, 69 centimeters. I have no idea. Okay, 66 centimeters, and then we'll measure the weight of the snake. 100. I don't know how much a snake should weigh, so I'm completely making stuff up. So please don't get mad at me and say these numbers are totally unrealistic. They are, because I've made them up. And so anyway, we would graph these, okay, and we can create a scatter plot. And on one axis, you would put one of the variables. So let's put length on the x-axis, and we'll put weight on the y-axis, and I don't know what, let's say 60, and let's say 64, 66, 70. Okay, is that right? 2, 4. Oh no, I'm totally numbering these wrong. 68, 72. Okay. All right, and then I don't know. Okay, so you have numbers here. Let's say 130, 150, 170. Oh, I'm gonna run out of space. Okay, so anyway, you would plot something here. 69 and 198 would be somewhere up there. 66 and 191, somewhere there. Okay, and then maybe you have other, you know, more observations, or whatever these things are. Okay, and then so you'd plot these different things, right? The different observations, right? And the overall question, and this is the big picture of the class or of today's lecture is, you know, is there a relationship between a snake's length and its weight? Okay. And the answer is yes, in general. Snakes that are longer tends to weigh more than snakes that are shorter. Okay. And that's let's make a new folder. Okay. And that's pretty much the premise of today's class is we want to describe relationships like this, and we're going to just be a little bit more specific. So rather than just say longer snakes mean heavier snakes, you know, we're going to be more specific, and we'll say if a snake is 1 centimeter longer than another snake, we would expect its weight to be, I don't know, 10 grams more than the other snake. Okay, we're just making stuff up, but that's you know, we want to be able to be specific in our description, and that's what chapter 12 is all about. Okay, so this is, we're looking for some kind of relationship. So we say, yeah, a longer snake tends to weigh more than a shorter snake. Okay, that makes sense. And can we be more specific? Can we assign numbers to that? And that's what we're going to look at today. All right, so let's get into names for variables. All right, and so as you read different textbooks, all right, we have names for the x variable and names for the y variable. All right, and so the x variable is often called the explanatory variable, and y might be called the response variable. Okay, other names you have the predictor variable, and y would be the predicted variable. Okay, sometimes x will be called the independent variable, and y will be called the dependent variable. Now, this is my least favorite. Okay, I don't like this. It exists in the literature, but I don't like it. Just because, you know, independent and dependent, to me, that doesn't make sense. If there's a relationship one way, there's a relationship the other way too. Okay. Sometimes we also have the, we might call x the input variable, and y might be called the output or outcome variable. Okay. And so these are all different ways to say the same thing, really. Okay. And in all of these, we use the x variable to quote unquote explain or predict the y variable. Okay. And when we use the word explain, what we're not saying how the relationship works or why it's the way it is. We're not trying to get at any kind of cause and effect relationship or explanation there. All we're saying is that, if we're able to explain, kind of in the way that when we did ANOVA, we're able to explain some of the variation. We're trying to say that, if we take into account this other variable, we can maybe improve our prediction for the other variable. We can improve our prediction for y, right? So let me just kind of jot all of that down. Okay, so explain just means we're trying to improve, maybe even just slightly, our prediction for y. Okay, and what we mean by improve our prediction for y, it's kind of this idea. If you had no information, right? I say, I've got this. I have a snake in this box here, right? What a terrible game to play. But we're going to say I have a snake in this box, and I want you to predict how much the snake weighs. And you go, this is a ridiculous game. This is a ridiculous premise, right? Please, just try to predict how much the snake weighs. So you say, well, I happen to know that the average snake weighs 190 grams. So you'd say, well, that's my prediction. I'm going to predict 190, right? And it's a safe bet to predict average. And then I say, let me give you a piece of information. The snake that's in my box, it's longer than average. Do you want to change your prediction? And you go, oh, well, if I know that the snake is longer than average, yeah, I want to change my prediction. I want to say the snake is going to weigh more than average, right? And so the fact that we would change our prediction based on this new information indicates to us that the length of the snake explains something about the weight of the snake, okay? That if we know the snake is longer than average, we would change its prediction to be heavier than average, okay? And that's basically all that we're trying to say here. So, example, predict the weight of a snake. Okay. Given no other information, the quote, the best guess will be to predict the average weight of snakes. Okay. I tell you the snake is longer than average, okay? And so the fact that we would make an adjustment indicates to us that, yes, that the length of the snake explains the weight, okay? On the other hand, if I gave you some other information about the snake and I say, oh, you know what, this snake, the name of the snake has 7 letters in it, all right? And the average snake name only has 5 letters in it. So this snake has 2 more letters than average in its name, okay? Would you make an adjustment to your prediction? And you no, right? Knowing how many letters in this are in the name of the snake doesn't help us, okay? And you can say, oh, you know, no, my snake has 20 letters in its name. It's, you know, whatever, right? And that's not going to help us, right? So the number of letters in the name of a snake does not explain anything about its weight, okay? So we would not make any adjustments there, right? So okay, so anyway, snake is longer. So length explains the weight. Okay. All right, so, you know, when we're talking about relationships between variables, there's a few things that we can describe, okay? All right, so all right, so we have first the form or shape. And as far as our class goes, we will look at either linear versus nonlinear. Right, and then we have the direction. And we have the strength. All right, so form, if we use linear, linear means the overall relationship can be described by a straight line. All right, so you might so you have data that kind of go up around a straight line. This would be linear. And then going in the opposite direction as well. Huh. Okay, so both of these would be linear. Okay. And then nonlinear basically just means, you know, a straight line is not enough. So you could have something perhaps, you know, data that look like that. Data that look like that. All right, space over here. I don't even have. Well, there's all sorts of nonlinear relationships, okay? And basically, nonlinear would be, you know, a straight line is not enough. Straight line cannot describe relationship. Okay, so our class will only look at linear relationships. Okay, and tools like correlation, when we're going to learn Pearson's correlation, you know, it only makes sense to apply to a linear relationship, right? So do not use tools intended for linear relationships do not use tools intended for linear relationships on non-linear relationships. Okay, and best method to decide if something is linear is to graph it and look at it. Okay, our eyes are very good at detecting like straight lines and patterns and things like that. Okay, our eyes are very good at that. So the best tool is to look at it and ask, does it kind of look like a straight line? And you can kind of say, yeah, it looks kind of like a straight line, and that's going to be the best. Okay. All right. First view quiz answer. First view quiz answer is the letter B. B as in bear. B as in bear is your first view quiz answer. So jot that down. That is your first view quiz answer. First view quiz answer. B as in Bruin. Okay, that's a good suggestion there. Okay. All right. Let's talk about the direction. Okay. Direction, you have positive and negative, and neither positive nor negative. Okay, so positive means overall, large X goes with large Y. And small x goes with small y. Okay, so an example would be snake length and snake weight. Okay, so let me. Yeah, X and Y. Large positive direction means something like this, okay? Overall, if you look at this area down here, this is where you have small x, and it corresponds to this side, you have small y, okay? And if you look up here, these are large values of x, and they go with large values of y. All right, so that's positive direction. Okay, negative direction is just kind of the opposite. Overall, large x goes with small y, and small x goes with large y. All right, so points that go like this. Okay, here's x, here's y. All right, so if you look at over here is small x on the low side of x, but we're at large y. And then over here, this is large x, but small y, okay? And so an example of negative direction would be something like used car mileage and resale value. Okay, so a car that has low mileage, it's only driven, 2,000 miles or something on it, you can expect to sell it at a higher value. Whereas a car with high mileage, so a car's been driven, 90,000 miles, 120,000 miles on it, it's going to sell for less value, right? Just because it indicates that it's been used a lot more. So that would be in negative direction. Large x goes with small y, small x goes with larger y. All right, and then we can also have neither positive nor negative. Okay. And this basically means no, well, not no relationship, but we'll just say neither positive nor negative, okay? So we have a few examples here. X and Y. So X could be, maybe we'll have age, and Y will be how many fingers does someone have, okay? And so over time, we can look at, does the number of fingers someone has change with age? And it does not, okay? I mean, at least for this particular person, right? And so there's no relationship there, okay? No, neither positive nor negative. Right here we can have say time, and we'll say altitude. Maybe we're looking at a toy rocket. And it goes up, and then it comes down, okay? All right, and it's important to note there is a relationship. So just because it's neither positive nor negative doesn't mean that there's no relationship. There is a relationship, okay? but it cannot be, but it is nonlinear. And positive or negative is not sufficient to describe it. Okay, but there is a relationship. All right, let's do one more. That is neither positive nor negative. We'll have shoe size and GPA, okay? So we look at different students. We ask, how big are your feet? Okay, or maybe what size shoe do you wear, okay? And then we also ask, what is your GPA? And I don't know what we'll see, but we're not gonna see a real relation. We shouldn't see a relationship here, right? You're gonna have students with big shoes that have high GPAs, students with big shoes that have low GPAs, students with average size shoes that have high GPAs, students with average size shoes that have low GPAs or average GPAs, students with little shoes that have high GPAs, and students with little shoes with low GPAs, and so on and so forth, okay? So these are neither positive nor negative there, okay? And here I would say there's no relationship, but we have that, okay? All right, let's talk about the strength. Okay. Strength of a relationship. Okay, and strength of a relationship, we can think of this as how good, or how close will our predictions be? Okay. So how good will our predictions be? Okay. And so here, let me just plot. All right, so one, we're gonna have, you know what, we can also think of not just how good will our predictions be, but how much scatter is there? Okay. So here we're gonna have so here there's a lot more scatter. Okay. So this one is strong, and this one would be weaker. Okay. This one is, there's little scatter. And the red line, red line represents our predictions, okay? Okay. And over here, when the relationship is strong, we can expect the actual values to be close to our prediction. Okay, weaker, there's lots of scatter. And, the actual value, the dots could end up being far away from the prediction. Okay, so that describes the strength of a relationship. All right, and so, strong and weak, that's fine, okay? But just like everything else in statistics, we like to give things a numeric value, right? So rather than just saying lots of spread and little spread, we have the variance and the standard deviation, which gives a numeric value describing exactly how much spread there is, okay? Similarly, rather than saying the relationship is strong or the relationship is weak, we can exactly quantify how strong or weak the relationship is by using something called the correlation coefficient, or just simply put, the correlation, okay? So we quantify the strength and the direction, the strength and direction of a relationship with the correlation coefficient. Okay, or we just call it correlation. And technically this is known as Pearson's correlation. There's also Spearman's correlation, Kendall's correlation. There's other correlation values, but this is the most commonly used one. Someone talks about correlation, they're talking about Pearson's correlation. The symbol for correlation is a lowercase r, and r is always between 1 and -1. Okay, r is always between r is always between 1 and -1 inclusive. Okay, and the sign of r is the direction of the relationship. So and if r is close to 0, the relationship is weak. And if r is far from 0, that is close to 1 or close to -1, the relationship is strong. Okay, r only tells us about the strength and direction of a linear relationship. Okay, and then a warning is it only makes sense to use r if the relationship is linear. correlation if the relationship is linear. Now, it's just the result of a formula, so you can still plug in values from a nonlinear relationship and you'll get a number back, but that number is not going to have meaning. And the number itself can't tell you if the relationship is linear or not, okay? So you can plug in values from a nonlinear relationship, but the result will not have meaning. Okay. And R by itself will not tell you if the relationship is linear. Okay, let me let me show you some examples of like what correlation will look like. And oh, let me draw a couple pictures here. So that, let me do this. And one more. All right, so I'm trying to draw dots exactly on this line here. Okay, so what is R here? Okay, what's the direction? Direction is positive. Okay. And how's the strength? Strength is very strong. Okay. Okay, it's very strong. There's absolutely no scatter. So because there's no scatter at all, or that's what I'm trying to draw, no scatter at all from the line, the R here is going to be +1. Okay. What about this one? I'm going to draw dots on this line as well. Okay. So what is the correlation here? What do you think? Do you think it's 1, a little bit less than 1, a little bit closer to 0? What do you think? Any guesses? The answer here, and I appreciate everyone's guesses, the answer is exactly 1, okay? For all of the exact same reasons that I wrote here, okay? In that direction is positive, it's very strong, and there's no scatter at all from the line. Now, you look at that and it feels, right, when you look at this, you say, well, the slope's a lot more shallow, right? It's like a lower slope, okay? That's absolutely true. The slope is more shallow, but R is not related to the slope. Okay, it only tells us about direction and strength. Direction and strength. So both of these, direction is positive, relationship very strong. There's no scatter at all from the line. So you're going to have R equal to 1 in both of those cases, even though the slopes are different. Okay, the correlation is not, doesn't tell us about the slope. Okay, what about this one? Here I've got dots totally flat here on this line. What is the R here? Okay, so this one, the direction is neither positive nor negative. Okay. All right, so even though there's no scatter, okay, even though there's no scatter, here, the fact that it's neither positive nor negative, right? The line is completely flat and horizontal. You're going to have an R equal to 0, okay? It's neither positive nor negative, so R is 0. And so this is kind of like the, is there a relationship between age and the number of fingers? There's no relationship there, okay? It's flat, okay? Direction is neither positive nor negative. So even though there's no scatter, the fact that there's that the direction is neither positive or negative puts R equal to 0. Let me share a picture here, or let me just, this is cut from the textbook. Oh dear. How's this working here? I hope this works, please. Okay. So here's a bunch of correlations from the textbook. Okay, this is from the textbook. Okay, and we can see correlation 1, different slopes, correlation 1, correlation -1, different slopes, -1. When it's flat, you have a correlation of 0. Okay, we also have correlations, a little bit less than 1. There's some scatter here. And as we increase the amount of scatter, the correlation goes from 0.8 to 0.4 to 0. And here we're at -0.4. Here we're at -0.8. All of these things over here, we have correlations of 0. And that doesn't mean there's no relationship. There's definitely a relationship in this plot. It's just using correlation would probably not be appropriate or sufficient to describe that relationship. Yeah, so here, is this relationship linear? I would say there's just no relationship. There's just no relationship here. So to use the word linear relationship, it doesn't quite work out in that, just because there's no relationship, okay, in this example, okay. Maybe, and just kind of a little bit of a warning here, a warning example. You could have a data set that looks like this. Okay, and in this case, for this data, R would be positive. Okay, and that's because if you were to try to fit a straight line, it would kind of try to do something like this, okay? And again, using correlation on a nonlinear data set will lead to kind of nonsensical results, okay? Correlation R on a non-linear data set will result in, kind of nonsensical results. Okay, let me go ahead and give you your second view quiz answer. Today's second view quiz answer is the letter D. D as in dog. D as in dog is the second view quiz answer for today. All right, let me copy another image here. This works. Okay, so we are going to talk about calculating R by hand, okay? Now, truth be told, no one really calculates R by hand, okay? In the same way that no one really calculates the standard deviation by hand, like I made you guys learn it. And today I'm going to make you guys learn how to calculate R by hand, and you'll be asked questions about asking you to calculate R by hand on your quiz and final exam. But the truth is we don't really do this. I think there's merit in learning. You'll see kind of like how we're getting these numbers, and so that's why we learn it. But the honest answer is we don't really do this by hand anymore. Wait, did I give you your second view quiz answer? I'm already confusing myself. Okay, second view quiz answer, just once again, is D. D as in dog is the second view quiz answer. Okay, all right. So here's the formula. The formula for R is 1 over n minus 1 times the sum of the product of z of x and z of y, okay? And so z of x and z of y, and this is x minus the mean of x over the standard deviation of x times y minus the mean of y over the standard deviation of y, okay? Maybe I'll put little subscripts, x I and y I. And we can actually factor out some of these values here. So we can 1 over n minus 1. Standard deviation of x is a constant for all of the values. The standard deviation of y is a constant for all of the values. So here we've got the sum of xi minus x bar times yi minus y bar. This is going to be for all n observations from I equal 1 to n. So let's, here's the data set, and I've got a very small data set, 4 values here, but let's go ahead and do this here, okay? We got x, make a few columns here. Okay, so I've got x, I've got y, all right? And so our first data point is the 0.12. The next data point is the 0.26. The next data point is the 0.34. And the last data point is the 0.48. Okay. And the mean of x, if you add up these numbers, you get 10 divided by 4. You get the mean of x to be 2.5. And then, if you recall, the standard deviation is the square root of y minus y bar over n minus 1. If you go through and you calculate the standard deviation of these 4 x values, you get 1.291, right? You do the same thing for y. The mean of y is 5, and the standard deviation of y is 2.582. Okay, so what we're going to do is we're going to calculate each x minus the mean. So I do 1 minus 2.5. I get negative 1.5. 2 minus 2.5 gives me negative 0.5. 3 minus the mean is positive 0.5. And 4 minus the mean is positive 1.5. Right? We do the same thing for the y's. We're going to subtract off the mean of y from each value. So the mean of y is 5. So 2 minus 5, negative 3. 6 minus 5, positive 1. 4 minus 5 gives me negative 1. And 8 minus the mean 5, positive 3. Okay. And now I'm going to take the product of xi minus x bar times yi minus y bar. Okay. So I've got negative 1.5 times negative 3. And that gives me positive 4.5. Negative 0.5 times positive 1 gives me negative 0.5. 0.5 times negative 1 gives me negative 0.5. And 1.5 times 3 gives me positive 4.5. All right, and so if we add all together, we will get the sum of xi minus x bar times yi minus y bar. The sum is going to be equal to, so if you add all of this up, we get 8. We get 8, okay? And so the correlation R is 1 over n minus 1. We have 4 observations. We subtract off 1 times 1 over the standard deviation of x, 1.291, times 1 over the standard deviation of y, 2.582, times this product here, 8, okay? And when you do all of that, you get a correlation of 0.8. And that's how we would go about calculating the correlation by hand. Okay, can I flip my slide to the next page here? Okay, I'm going to go ahead and do it. All right, so let me let's talk a little bit about this. Okay, so kind of a key idea here is, you know, we want to look at what is like the average value of x, right? Average x is x bar 2.5, and average y is y bar, which is 5. Okay, so I'm going to draw a couple lines. Showing where average x is and average y, okay? So this is y bar equal to 5, and this is x bar equal to 2.5, okay? Let's take a look at our 4 data points. We have 1 for x and y. We got 1, 2. We have 2, 6. We have 3, 4. And we have 4, 8. Okay. Let's look at this first. Actually, before I do that, all right. So remember, positive direction is large X goes with large Y and small x with small y. And negative direction is large X with small y and small x with large y. Okay. And what we will, when we use the word large, that's basically gonna mean above average. And small will mean below average. Okay, so let's look at this value here. Okay, our first, the first value down here, 1, 2, okay. This is small x and small y, right? It's like x is below average and y is below average, okay? So we've got small x, small y. This will be, maybe I will write very small x and very small y comparatively, right? Because it's like way below average, okay? And so we got very small x, very small y. This will be large positive contribution to R. Okay, let's look at this observation over here. Here, you know what? Let's. What did I do? Let's look at 4, 8. Same idea here. This one, this point out here, x is 4 and y is 8. This is very large x. And very large y. And so this will have a large positive contribution to R, okay? If we look at the other points though, we have this point, 2, 6, and this point, 3, 4, okay? Okay, 2, 6 is, slightly small x. It's a little bit below average, slightly large y. Okay, its y is a little bit above average. Okay, so this will have a small negative contribution to R. Okay, over here, the point 3, 4, we have a slightly large x going with a slightly small y. Okay, the y is slightly below average. So this will have a small negative contribution to R. Okay, because it's this one, slightly above the x average and slightly below the y average. All right, and so overall, the positive contributions outweigh the negative contributions. Positive contributions, which are the green arrows, outweigh the negative contributions, which are the red arrows. Okay. So the overall correlation is positive. Okay, does that make sense? What's happening here? So overall, so you look at, are we above average in X? Are we above average in Y? Are we above or below average X? Are we above or below average Y? And you kind of look at that magnitude, and what we see is, the green arrows, which are in the positive direction, outweigh the red arrows, which are in the negative direction. Okay. And just to kind of, reiterate this, I'm going to just do a very quick example. Where I'm going to delete this point and delete that point. And I'm going to draw in a point right here and draw in a point right here. Okay. And so just real quick, we can just do like a quick computation here. And I think we'll see the results. So here are my X and Y. X, I've got 1, 2, and 1, 8. And over here, we've got 4, 2, and 4, 8, okay? And so, if we calculate X bar is still 2.5, and Y bar is still 5. Okay, so this is what we have. We can look at the green lines here. Red. Okay, and we can see that they're going to kind of cancel each other out, right? So if I do xi minus x bar, we're going to get 1 minus 2.5. We get negative 1.5. I'll get negative 1.5, positive 1.5, positive 1.5, right? And if I do yi minus y bar, 2 minus 5 gives me negative 3. 8 minus 5 gives me positive 3. Here I'll get negative 3 and I'll get positive 3. And the product of these differences, okay, here I get negative 1.5 times negative 3, I will get positive 4.5. The next one I will get negative 4.5. Here I will get negative 4.5. And here I get positive 4.5, right? And we can see that if we do the sum of all of these values, we're going to get 0, okay? And so the correlation, which is 1 over n minus 1 and 1 over standard deviation of x times 1 over the standard deviation of y, whatever it is, it doesn't matter. This part's 0, right? The correlation is just going to be 0. Okay. So here we can see the positive contributions in green perfectly cancel out the negative contributions in red. And so here the overall correlation is 0. Okay. And we can see it for these 4 data points. And pretty much the same principle holds. It's just you get a larger data set, 100 data points, 1,000 data points, and the same kind of idea holds. All right. Some of the data points will have a positive contribution, some will have a negative contribution. And, basically we're just kind of measuring the total amounts of positive and negative contributions. And that's that. Okay, does that kind of make sense? All right, and so on a quiz, on this weekend's quiz, and then on the final exam, I'll have you calculate correlation by hand. And at most, you'll have maybe 5 data points, okay? Just because if you have anything more than 5 data points, the the calculations get very tedious and it's not fun to do. Excuse me. Okay, so we have a hypothesis test. Okay. Actually, excuse me, I need to blow my nose for a second, so just give me a second. Okay, so we have a hypothesis test for significant correlation. And so, if I use the same data set, okay, we have correlation equal to 0.8 for the 4 data points. And kind of the question is, if our sample is randomly drawn from the population, do our data provide evidence that the correlation between X and Y is not 0? Okay. Do our data okay? Or, another thing is 0.8 significantly different from 0? Or could it be the result of random chance? All right, and so our null hypothesis is rho equals 0, and our alternative hypothesis is rho does not equal 0. Okay, so this is the symbol rho. It's kind of the correlation in the population. It looks like a P, but it's the Greek letter for R. Kind of. Or R is the Latin letter for rho, whichever one you want to say. And so, our null hypothesis, we're basically saying that there's no correlation between X and Y in the population. And the alternative is saying that there is. Now, and you can also have a directional one. Okay. And so our p-value would be, in the interpretation would be the probability that a random sample of 4 data points would have a correlation of 0.8 or something more extreme or more unusual. So that would be R greater than 0.8 or R less than negative 0.8 if there were no correlation between X and Y in the population. Okay. The test statistic is given by this formula. T is equal to R times n minus 2 divided by 1 minus R squared. Okay. And you look up in the T table with n minus 2 degrees of freedom. Okay. N minus 2 because 2 points define a line. So if you only had, if your data set only had 2 points, you would always have a correlation of 1 or -1, right? Because they're always going to be in a perfectly straight line. So it's not until you have add a third data point or a fourth data point or something, until you have a third data point that you can even talk about, is this correlation possibly from random chance, or is it like for real? Okay, so let me go ahead and do this, right? So we have R equal to 0.8. We have 4 data points. So our test statistic is going to be 0.8 times the square root of 4 minus 2 divided by 1 minus 0.8 squared. So I get 0.8 times the square root of 2 divided by 1 minus 0.64 is 0.36. And here I get 1.886, and we have degrees of freedom equal to 2. Is that okay? And so let me go ahead and pull up my reference table. Where did I put that? Okay, so T distribution, here we go. 2 degrees of freedom, 2 degrees of freedom, 1.886. So this is, I'm always excited for this example because we get the exact value in the T distribution. Normally it's always between values, but here we actually get the value. And so we can say our tail area is exactly equal to 10%, okay? So it's not between 10 and 5% or not between 20 and 10%. It's exactly equal to 10%. So the tail area is equal to 10%, okay? And the alternative is non-directional. So our p-value is exactly equal to 20%, all right? And so if alpha is equal to 5%, we would say we do not have evidence that there's correlation, or I would say we do not have maybe enough evidence that there is correlation between X and Y in the population. Barely fitting it on the page. Okay. Is that all right? And you might feel like that's strange. We got a correlation of 0.8, and you're telling me that 0.8 is not significantly different from 0. Like how much more correlation do we need to have for me to say that there is correlation? Well, part of the issue is that we only have 4 data points. We only have 4 data points. And so you can imagine, you blindfold somebody, you give them 4 darts and you just say, throw these 4 darts at the wall. And is it possible that just kind of by random luck, the 4 darts end up looking like they're kind of in a straight line, that they have a correlation of 0.8? And the answer is yeah, something like that's going to happen with a probability of about 20%. Okay, so with a probability of about 20%. Okay, yeah. Oh, the question about this p-value. Yes, the p-value is 2 times the tail area because the alternative is non-directional. And when you use the t-table, your the table gives you the single tail area, and when you have a non-directional test, you take the one tail and you double it. Okay. Question says, to generate an interpretable t statistic, we need at least 3 data points. Yeah. Yes. So yeah, you cannot do a test for significant correlation if you only have 2 data points in your line, because they'll always be in a straight line. So there's no test there. Okay. You need at least 3 data points in order to even ask the question, is the correlation significant? Question, is it possible for the alternative to be directional? Yes, you can have a directional alternative that says, also possible. You can have the correlation is greater than 0, or the correlation is less than 0, right? And you would say, and then you would just leave your tail area as your p-value with a directional test, assuming that the correlation, right? So if you say, if the alternative was, do we have evidence that the correlation is negative, is less than 0, and our correlation, our correlation is 0.8, the answer is going to be no, we don't have evidence of that, right? Because my correlation was positive, and you're asking, do we have evidence that the correlation is negative? The answer is no, right? But if we said, do we have evidence that the correlation is positive, and my correlation comes in 0.8, then we would go through the test. My tail area would be 10%. I would leave it as is, and my p-value would be 10%. And I would say, well, we don't have enough evidence to reject the null hypothesis. We don't have enough evidence to say that there is correlation between X and Y in the population. Because with only 4 data points, we could get this result of, what appears to be correlation. It's possible that it happened just by random chance, because, it's possible that it happens by random chance. It could happen, we could get a positive correlation, something like this, about 10% of the time, and you would get a negative correlation, something like that, about 20%. Yeah, either positive or negative, could happen 20% of the time. Okay, I'm going to run out of time. I might go a little bit over the end of 5:50, so I will make sure I give you your third view quiz answer before I get there. But I've got to cover a little bit more stuff. Okay, we got to talk about linear regression. And this is basically finding the best fit line. Okay, and let me copy a couple pictures here. Copy a picture. All right, so here is our example. We've got X and Y, and I've got in my diagram here, I've got 2 candidate lines. So again, here, our X and Y is we've got the points 1, 2, 2, 6, 3, 4, and 4, 8. Okay, and here, this red line has the equation y equals to 2x, okay? So y hat is the fitted line, is the fitted line, okay? And here, y hat has the equation 1 plus 1.6x, right? All right, and this is maybe just to give it a little bit of context, I'm going to completely make something up, and this is a little bit silly, but we're going to say X represents the number of bedrooms in an apartment or house, and Y will be the number of closets. Okay, so, you know, you could look at a 1-bedroom apartment and maybe it has 2 closets. You can look at a 2-bedroom apartment, maybe it has 6 closets. You look at a 3-bedroom house, maybe it has 4 closets. You look at a 4-bedroom house, maybe it has 8 closets or something like that. And now we're going to try to fit a line, right? And so the question is, which line is the best? Okay, and the way we're going to, our evaluation criteria is pick the line with the smallest squared residuals. What? All right. And this gives us, have you heard of the term least squares regression? Least squares regression? Maybe you've heard that, maybe not. Okay. That's this idea here, okay? So we're talking about squared residuals, and we want the line with the smallest squares of residuals, okay? So what is a residual? First of all, a residual is kind of how off our prediction is from the actual value, right? How different is the prediction from the actual value? So we want our predictions to be as close as possible to the actual value. So we want small residuals. How different is the prediction from the actual value? Okay, and so a residual will you define as the actual minus the predicted, okay? The difference between the actual value and the predicted value. Okay, or we could say symbolically, this is known as E of point I is yi minus y hat I, okay? Where E sub I is residual of point I, yi is actual value of point I, and y hat I is the predicted value of point I. Okay, so the residual is the actual value minus the predicted value. Okay, and what we want is we want the smallest of the, we want the line that has the smallest squared residuals. Okay, so let's copy. Let's take a look at this line right here. Okay. This one. Okay, gut feeling. What do you guys think? The one on the left or the one on the right? Better fit line. Left or right? Left or right? well, let's take a look. Let's take a look. It's right here. Okay. All right. So here the prediction line y hat is equal to 2x. All right. So we have x and we have actual y. We have predicted, which is y hat is equal to 2x. Okay. We're going to have the residual, which is going to be y minus y hat. And sorry, my lines are so terrible. And then we've got the squared residual. Should have used the straight line tool. Okay. So our actual values are 1, 2, 2, 6, 3, 4, and 4, 8. Okay. So the predicted value, right? I would do 2 times 1. I predict 2. For this next point, I predict 4. I take 3 and I multiply by 2 and I predict 6. And for the last point, I would predict 8. Okay. So how much is my residual? All right. Here, I have no residual. Okay. Because my actual and my predicted are exactly the same. Here, my actual is 6. My predicted is 4. So I have a residual of 2. Here, my actual is 4. My predicted is 6. So I have a residual of -2. And here, I have a residual of 0. Okay. The squared residual, I take 0 and I square it. 2 squared is 4. -2 squared is 4. And 0 squared is 8. So the total squared residuals is equal to 8. Okay. And what we can think is, let me draw a little let me draw a square here. A square there. And a square there. Okay. Maybe I'll draw a straight line here. Okay. So this part is the residual. Okay, it's the difference between the actual value and the predicted line. And then this square, the area of the square, maybe I'll shade it in red. Oh, that's not what I need to do. Oh dear. Okay. Something like this. Okay. It's kind of hard. All right. The area that I'm shading in here, this is the area of the squared residuals. Okay. Okay. So the shaded area is equal to the total squares of residuals. Okay. So that's, so we have a total squared residual of 8 for this line. Let's look at the other candidate line, which let me copy that from my image over here. So here, my prediction line is 1 plus 1.6x. That's straighter lines here. That's y hat, the residual, and the squared residual. Okay, so I've got x. We have actual y. We have predicted, which is y hat is equal to 1 plus 1.6x. We have the residual, which is y minus y hat. And then here we have the squared residual. Okay, and our data points are 1, 2, 2, 6, 3, 4, 4, 8. Okay, so the predicted value here is 1 plus 1.6 times 1, and I get a predicted value of 2.6. Then I have 1 plus 1.6 times 2, and I get a predicted value of 4.2. I have 1 plus 1.6 times x, which is 3 now, and I get 5.8. And I have 1 plus 1.6 times x, which is 4, and I get 7.4. Okay, so the residual is 2 minus the prediction 2.6. I get negative 0.6. 6 minus 4.2, I get 1.8. 4 minus the prediction 5.8, I get negative 1.8. And here I get 8 minus 7, oops, 8 minus 7.4. I get positive 0.6. Okay, the squared residual, negative 0.6 squared gives me 0.36. 1.8 squared is 3.24. Negative 1.8 squared is 3.24, and 0.6 squared is 0.36. And the total squared residuals is, if you add all of these up, 3.36 plus 3.24 is 3.6. You get another 3.6, you get 7.2. Okay, so if we were to draw boxes here, boxes would look something like this. Square there, square there, square there. It's hard to let's go here. Okay. So the total of the total shaded area here is 7.2. So this line, this prediction line, has less less, I guess, total squared residuals. Okay, and so it'd be considered, it is the better line. Okay, using the definition for least squares regression. Okay, so least squares regression is the idea that you're looking at the residuals, you're squaring them, you're looking at kind of the total area of these squared residuals, and you want the line. So yeah, you know, when you look at it, okay, it often when I first presented these pictures, a lot of you kind of have this gut feeling that the line on the left, where did that? So I showed these two lines here, and I said, you know, which one's the better one? The one on the left, it looks like, oh, you know, it does a better job because it fits these ones perfectly. But when the effect of squaring the residuals has the effect of kind of like magnifying larger things. So like when you square residuals, it's better to be off by a little bit a bunch of times than to be off by a lot one time. So if you're off by 1 10 times, you know, 1 squared is 1, and you have 10 of those, that adds up to 10. Okay, that's being off by 1 10 times is better than being off by 10 one time. So if you're off by 10 one time, 10 squared is 100. So you would have a total squared residuals of 100 if you're off by 10 once, then a total squares of 10 if you're off by 10 separate times. And so, so anyway, the overall effect is, you end up trying to minimize these larger errors. When I gave you these two candidate lines, I already knew what the answer is. Okay, and that's because for linear regression, okay. Let me just give you your last view quiz answer. Last view quiz answer is A. A as in apple. A as in apple is your last view quiz answer. A as in apple. Okay, and I apologize. I'm just going to go over my time here a little bit. Okay, so if you need to sign off, you got other things to do. No offense. Just please watch the last few minutes of the video. But I'm going to keep going on here. Okay, so last view quiz answer is A. A as in apple, and I've got a couple more pages to write here. Okay, so for linear regression. The best fit line will always have the following slope and intercept. Okay. So the slope B1 is equal to the correlation times the standard deviation of y divided by the standard deviation of x. Okay. And the intercept B0 is y bar minus B1 times x bar. Okay. And you must find the slope first. Okay. And then the prediction line is y hat equal to B0 plus B1 times x. Okay. Prediction line always passes through the point x bar, y bar. Okay, so when we had our data set, x and y, 1, 2, 3, 4, 2, 6, 4, 8. Okay, we had x bar is 2.5, y bar is 5. Standard deviation of x was 1.291. Standard deviation of y was 2.582, and the correlation was 0.8. Okay, so the best fit line, the slope B1 is equal to 0.8 correlation R times the standard deviation of y, 2.582 divided by the standard deviation of x, 1.291. You get a slope of 1.6. Okay, the intercept B0 is equal to y bar minus B1 times x bar. So you're going to get 5 minus 1.6 times 2.5. You get an intercept of 1. So y hat is going to equal 1 plus 1.6x. That's the best fit line. Okay, so let's try using this. So we'll say if a place has 2 bedrooms, how many closets do we predict? Okay, closets is y, bedrooms is x. Okay, so we got y hat is equal to 1 plus 1.6x. And we have y hat is equal to 1 plus 1.6 times 2. And we get 4.2. We predict 4.2 closets. Now, that's our prediction, okay? You can have a decimal in the prediction. Okay, of course, actual values will only be whole numbers. Actual values in this example. So depending on the example, you can have decimals or not. But in this example, actual values in this example will be whole numbers. You know, 4 closets, 3 closets, 5 closets. Okay, but if you look at many places with 2 bedrooms, look at many 2-bedroom dwellings, and average all of the closets, we expect an average of 4.2. I do a couple things. Okay. Interpretation of the slope. Okay. This is going to be how much we predict y will change if x goes up by 1. Okay. So this would be if the number of bedrooms goes up by 1, our prediction for the number of closets goes up 1.6, right? My slope is 1.6. If x goes up by 1, our prediction for y goes up by the amount of the slope, okay? But this is important. Do not think of it as modifying an observation's x value, okay? Okay, you can't take a person and increase their height by an inch, right? You can't take a snake and just stretch it out an extra inch, right? We can't modify an observation's x value. What it is if you have an observation with snake length 60 and you have another observation with snake length 61, how different is your prediction for this than your prediction for this, right? It's kind of a, how different are your predictions for 2 different observations with different x values? It's not, you can't think of it as taking an observation and then, you know, inducing some kind of change in the x value, right? So do not think of modifying an observation's x value. The slope tells us how much our predictions will be different for different observations with different x values. Let me do interpretation of the slope. Or not slope, of intercept. Okay, this is our prediction for y. If x can be 0. Okay, sometimes it makes sense for x to be 0, sometimes it does not. Okay, so, you know, if a place has 0 bedrooms, we predict 1 closet. If okay, that actually kind of makes sense because you can have like a studio apartment with like 1 closet, and I guess that would be a 0 bedroom place. I don't know. But then like nonsense would be if a snake has length 0, dot, 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 you know, our prediction is this, right? You can't have a snake with length 0. That's no snake, right? So that's just not gonna work. Okay. Oh, I'm like out of time. Okay. Usually I leave like, I have a bunch of warnings on the last page. Here, I will just copy this picture that I drew, or this slide that I have from another class. Okay. Last course class. Okay. There we go. These are warnings, and I'll just kind of drill through them real quick here. Number 1, use linear regression only if the relationship is linear. And we already talked about this, but common mistake is people start plugging these things in for things that are nonlinear, and it's just not going to work. Okay. You know, it only makes sense if you have numeric variables. So, you know, it doesn't make sense to try to do linear regression on something like a zip code or an area code or something where it's been coded as numbers, but it's not actually numbers. Outliers can drastically affect your results, right? So if we're looking at something like shoe size and income, there should be no relationship between shoe size and income. But, you know, let's say Shaquille O'Neal is in your data set. Shaquille O'Neal has huge feet, very, very big feet, very high income. And then suddenly it looks like there's a relationship between shoe size and income, okay? And then the other warning is do not extrapolate. Extrapolating is assuming that a linear relationship will continue on forever and making predictions where you haven't collected any data, right? So a silly example is, let's say you have a child and you've been measuring how tall your child is every month for the last 10 years, okay? And every month for the last 10 years, your child is getting taller every single month, right? And so you say, oh, okay, by the time my child is 80 years old, he's going to be, you know, 20 feet tall, right? Doesn't make sense, okay? We know that people keep growing until they're like somewhere, they stop growing somewhere between age 14 and 20, and then they stay kind of the same height for the rest of their lives, pretty much. And you know, that's familiar to us. We know that things level off at a certain time, but for a lot of other things, we don't know what's going to happen. And so it's really hard to know that if a linear trend, even if it's held for the last 10 years, last 20 years, it may not hold into the future. And so it's really dangerous to kind of, or it's unwise, I should say. It's unwise to extrapolate and assume this relationship will hold forever. Okay, sorry so much. And thank you so much for your patience, for sticking around. Going over time way too much today, but that's it. That's it for today's lecture. Thanks for holding out. And again, on Friday, I'll have a review session. So we'll see you guys on Friday. It's been a pleasure being your, if I don't see you guys on Friday, it's been a pleasure being your professor this quarter. I hope you guys enjoy the class, and good luck as you guys study for the final exam. We will see you on Wednesday. Oh, if you missed your view quiz answer, the last view quiz answer was the letter A, Okay. All right. Have a good night. Thank you, everybody. Again, I'll stick around also for office hours. So if you have any questions, I'll be around to answer those questions. Okay. Have a good night. Thank you. Thank you again for sticking around and being patient with me here.